Great. Well, thanks very much for having us today. We're going to be providing a bit of an overview of what a life cycle assessment of concrete pavement entails, how that information is evolving, and some of the gaps that are holding back some more accurate assessments of real-world projects. We'll also be providing a bit of an overview of the more general sustainability benefits of concrete and why carbon doesn't necessarily tell the whole story. Guiding a lot of the discussion today is the Athena Pavement LCA calculator. This is a free web-based program that allows users to sign up for an account and assess different pavement alternatives by outlining the geometry of the road and entering or selecting region-specific data in terms of materials, haul distances, and equipment for construction and maintenance activities. It's a good tool, one that provides a lot of sophisticated calculations, but like any computer model, is really limited by the accuracy of its inputs. The calculator has a lot of built-in defaults, which definitely makes it a lot easier for the user to become familiar with the tool and its outputs, but there really needs to be a strong understanding of how representative those default values are and whether more accurate real-world data might be available to inform calculations. So outlined on the screen here are some components of a pavement life cycle assessment, which includes the embodied effects associated with the manufacturing, construction, and maintenance of the pavement alternative under analysis. Much like with buildings, these embodied effects tend to receive the most amount of attention when discussing a carbon footprint. But as Jeremy alluded to, the use and end-of-life phases can be significant areas of a pavement LCA, particularly when emissions associated with traffic are considered. A little later in the presentation, we will be highlighting how the pavement alternatives can play a role in reducing these emissions. But first, we're going to examine the manufacturing side of the equation. And before you can assess a pavement, you really need to have a design, and optimizing that design to reduce the amount of pavement material required is an important step for both concrete and asphalt alike. In Canada, and Western Canada in particular, there are not a lot of concrete pavements relative to asphalt in transportation networks. And as a result, there's not a lot of design expertise either. And many designers have in their mind older design methods that require significantly thicker concrete structures than modern best practices. So by using more up-to-date software and modeling the performance of the pavement using a program like Pavement ME, the designer can realize significant savings in terms of that pavement thickness, which reduces both the cost and carbon implications as well. So the cement and concrete industry have been working for a number of years with road design engineers to develop a series of equivalent pavement reports that try to compare asphalt to concrete on an apples-to-apples basis. On our rediscoverconcrete.ca website, there are a number of provincial reports, including British Columbia, that examine the life cycle cost implications of roadways under a variety of traffic loads and subgrade strengths, using a 25-year design life and 50-year time horizon. To demonstrate what this means in terms of a life cycle assessment, I've pulled an example road from this report, a road with a subgrade strength of 50 megapascals and a load of 2,500 trucks per day. So this is what the cross-section of the different pavement alternatives would look like. As is generally the case, concrete requires less aggregate beneath the road structure, which is an effect that's amplified as traffic volumes are increased and the subgrade strength is decreased. So if, for example, the road were to see 10,000 trucks a day and be built on a 30 MPa subgrade, the asphalt structure would go from about 450 millimeters of total base course to 800, where the concrete structure would only increase from 200 to 300. What that means in terms of carbon, not all that much really, because the carbon footprint associated with local aggregates is generally quite small, so the advantage for concrete here is relatively small. As for the carbon intensity of the concrete itself versus asphalt, well, that really depends on where the information is coming from. So if you were a road designer using the best information you could find on the internet, you'd likely have an industry-level EPD at your disposal. And while this might be better than the defaults that are in the Athena program, it's still likely a very long ways from what you're actually seeing in your road project. There are a couple different tools that are very near to market that will help produce facility-specific EPDs, including the Global Cement and Concrete Association's EPD tool and the National Research Council's LCA Squared initiative. But in lieu of this information, designers are unfortunately stuck without the ability to really accurately represent concrete within the Athena calculator at this time, at least not without the assistance of someone from the cement and concrete industry to help them along. And when you look at the carbon intensity of concrete in general, it's important to have an understanding of what the concrete comprises. With most concrete being produced local to a project site, there are short haul distances. The mix includes a blend of local sand, gravel, and water. However, it's really the cement that drives up that carbon footprint. As noted on the slide and through Jeremy's presentation, despite making only up 10 to 15% of the total concrete mix, the cement contributes about 85% of the carbon intensity. So as an input, the carbon intensity of the cement is critical, and any carbon reductions the cement supplier is able to realize is going to have a significant impact on that concrete. What are those carbon reduction opportunities? Well, there's quite a few different initiatives that the cement industry has been working on recently, many of which are either in practice already in select geographies across the country or are within about 5 years of implementation. There are lower carbon cements like Portland limestone cement and the increased use of byproducts like fly ash and slag, which can reduce the carbon footprint of concrete by 30% or more. There's lower carbon fuels, which both Lafarge and Lehigh are using in BC currently, where waste materials like construction and demolition debris, wood waste, biosolids, and other materials offset the use of fossil fuels of coal and natural gas. And then there's a whole suite of carbon capture, utilization, and storage technologies that are either on the market or very near to market presently. The Lafarge Richmond facility is currently working with a company called Savante to capture carbon from their facility locally. And in Edmonton, Lehigh has a full-scale carbon capture project under development that would see up to 90% of its emissions captured when constructed in the next 5 years or so. These are very exciting technologies that are going to help the industry make significant strides towards the goal of carbon neutrality by 2050. What that means in terms of a pavement LCA, well, this is where the importance of project-specific information is best exemplified. So back in the 1990s, you'd probably see a carbon intensity somewhere in the order of what's outlined here for concrete. Whereas if you look at the industry level EPD for concrete at a mix similar to the equivalent pavement report that we're referencing, the global warming potential is somewhere more around here. But if you make some assumptions around the cement content of that concrete mix and consider the local cement facilities in BC with the industry leading practices they have in place, you're going to end up a lot closer to here. And then when you start to consider the use of Portland limestone cement, the increased use of low carbon fuels, slag substitution, you're going to keep realizing gains and end up somewhere around this zone. And then moving forward, as I indicated on the last slide, cement and concrete will be able to continue to reduce its carbon footprint using these CCUS technologies, continually improving towards that goal of carbon neutrality. How does this compare to asphalt? Well, again, it's going to be very much plant specific, project specific, but one data point we have here is from Athena in 2006, which is slightly better where concrete sits today, but it's relatively close, and that story is constantly evolving. So within 5 years' time, these LCA assessments are going to look drastically different than they do today. And it's not all about carbon, and the Athena calculator also looks at some other impact areas with regards to the environmental footprint of a pavement. Energy, for example, is an important consideration. And comparing concrete to asphalt, asphalt has significantly higher energy footprint, particularly when it comes to feedstock energy, which is highlighted here on the slide. Other categories that the Athena tool looks like include acidification potential, ozone depletion, and smog formation, which, depending on the local project conditions, may be of particular interest to a designer. And the Athena tool has a complete tabulation of all of these different effects as part of its assessment, which is pretty handy. Moving on from manufacturing and construction to maintenance, I'll just touch on this really briefly as it's the area that has the least amount of ambiguity associated with it. Roads, of course, need to be maintained. It would be great if a road stayed in its construction condition forever, but it deteriorates over time due to traffic, climate, and material performance. As such, routine and major maintenance is required, and these events are generally scheduled as part of a pavement preservation plan at the design stage of a project. The benefit of concrete versus asphalt is in the amounts of maintenance required over the lifespan of a roadway. In most cases, concrete requires significantly less maintenance events and activities than asphalt. And again, these equivalent pavement reports we have demonstrate this, along with outlining the maintenance schedules for various traffic levels that are being analyzed. And then here, using the Athena calculator to measure the impact of these maintenance schedules and the corresponding equipment and material needs, you can see that the asphalt alternative would have a higher carbon footprint than the concrete for this particular example, about 3 times as much, in fact. And with that, I'm going to pass over to Tim to carry on with the rest of the conversation.
Thank you, Shane. So you're going to have to change these for me, I think. So what I'll do now is I'll take a little bit deeper look in a few of the things that have already been discussed. Jeremy went over the pavement vehicle interaction. So basically, there's 2 things that we look at is the roughness and the deflection. The texture, actually, we're looking from that and on the safety point of view, and I'll have a slide in that shortly. So when we were looking at this, if you go to the next slide, please. The Dr. Zanussi did a study back in 1982 that showed a fuel savings of around up to 20% when operating on the concrete versus an asphalt pavement. And it was basically looking at that in the analysis of the deflection and the roughness of the pavement. So the Cement Association of Canada actually hired the National Research Council of Canada to look at this in greater detail from 1999 to 2000. And if you can see here, when you're looking at an asphalt pavement, it is a flexible structure. So it will deflect the load down in the base and the sub-base material, so you'll have a greater deflection of the pavement. And when actually the MIT work showed that you'd have to have 60% more asphalt to have the same deflection as the concrete pavement. So when you're moving from a pavement that has a bit of a bow wave in front of it compared to a pavement that doesn't, the way the concrete takes its loads, you'll have a fuel savings operating on the concrete pavement. So this is the study, the three studies. They looked at a van semi-trailer and a tanker semi-trailer to make sure they looked at both conditions to ensure that they did a complete analysis. And the results of the analysis is on the next slide, showed that the fuel savings ranged between 0.8% to 6.9%, depending on the speed that you're traveling at and whether you're a van semi-trailer or a tractor or a box semi-trailer. So when you look at this and you take a 62-kilometer section of roadway from Vancouver to Abbotsford, in 2007, it had 2.7 million tractor trailer units traveling back and forth on it. So if you take those numbers and calculate the fuel savings at the various levels that we have in the slide here, you can see that the CO2 at a 6.9% fuel savings gives you 13,700 tons of CO2 savings by having a concrete surface. And you also have the savings in dollars of around $4.3 million. And there's also savings in the reduction of the NOx and the SOx as well. Next slide, please. So if we look at MIT, of course, looked at this in more detail in the not just a few years ago, they started looking at it. And again, they started looking at the pavement vehicle interaction, and they looked at, again, the deflection and the roughness. And you can see when you're looking on the graph on the right-hand side, the roughness progression of the concrete pavement is very gradual. With the use of dowels preventing the joint deterioration and the joint faulting, you've got much better load transfer. So the pavement on the concrete has a very mild roughness progression, where asphalt will progress very quickly, and then it has to have an intervention, and then they'll again go up at a higher rate. So the concrete does have a lower fuel consumption. Next slide, please. So as was mentioned earlier, carbonation is another thing that's being investigated, and actually recent studies that are being undertaken at this time shows that the uptake can be actually as much as 40 to 90%. And this research is actually ongoing. So if you look at, it's much easier to look at a pavement rather than a building, because a building being the vertical structure, which might have material on it. The exposed surface of a concrete pavement can actually show the carbonation process, and you can actually go through and look at the Global Cement and Concrete Association tool, EPD tool, and it can give you a calculation of the carbonation that you can get based on 3 different alternatives. And you'll see the URL is on the slide, which you will be given these slides. Next one, please. So we always like to look at the circular economy, of course, when you're analyzing a roadway. The concrete pavements has a design life of normally 25 to 30 years, plus when you do maintenance interventions, the 50-year life cycle is a very common process. So at the end of the life of the pavement, what you want to do is you want to be reutilizing that material. So concrete pavement, you can actually crush that material and use it as a base in the new concrete, or you can actually, if it's good enough material, you can actually reuse it in a new concrete. And as mentioned by Jeremy, if you can stockpile this material or even spread it over a larger area, the more surface area that's actually available for the carbonation to uptake to occur, the better off you are in getting additional carbon savings. And with concrete pavements as well, part of the intervention is a diamond grinding during its life cycle. So you'll actually expose a new surface of area that can be used to, that will recarbonate itself as well. Next slide, please. So then we wanted to look at the concrete pavement itself. What are other benefits besides the longevity? Well, I mentioned about the fuel consumption and CO2 sink. As well as that, we have less fuel consumed during construction, because a concrete pavement has substantially less granular material underneath it. You can have a savings from the movement of truck movements back and forth, and actually the damage on your roadways is less as well. On top of that, You have recycled and industrial byproducts that you can use in the mix to improve the concrete properties, but also stabilize them in an area that you wouldn't have any issues with that you would in a landfill site. You also have a better albedo, so having a better albedo decreases the amount of urban heat island effect, and also the light reflectance is better, so your illumination is better. So it allows you to increase the safety in that area or decrease the lighting process. RCC was placed at a facility in Moncton, New Brunswick, where they decreased the lighting by 20% because they had much better lighting that way. Next one. Because you are a rigid surface, you're not going to have any rutting, you're not going to have any shoving, so you have an enhanced riding comfort. And then the key binder in an asphalt is liquid bitumen. Liquid bitumen is a form of energy, so you have a much higher energy footprint in a concrete pavement, in an asphalt pavement, pardon me, than you do in a concrete pavement. And the last one would be the hydroplane issue, which I actually have a slide, the next slide on, which will explain it a little bit better. Because concrete is placed in a plastic state, you actually can texture it the way you would you want to. So you'll do an astroturf drag or a burlap drag to provide a good texture on the surface, and it brings the fine aggregates, sand particles, to the surface. So high siliceous content of those aggregates provide you a very good skid resistance and a long-lasting skid resistance. And then when you look at the macro texture, you're putting the grooves in your pavement. And what that does is it increases the pavement tire interface, so that when you have water on your pavement, a tire coming over that pavement will push the water into the channels and away from the tire to improve your tire pavement interface and improve the safety on driving on that roadway. Next one, please. Now, an interesting thing that the Ministry of Transportation of Ontario has done is they've mandated a greenhouse gas emission reduction of 10% on any of their pavement projects. So they put that in their OPSS 1350 specification. One way that you can do that is just straight use Portland limestone cement. But what we would like to see in our industry is actually use the Portland limestone cement, but also use supplementary cementing materials, because the combination of the two will actually decrease the overall footprint of your pavement. Next slide, please. So then what can you do as the architect or the designer, the engineer that would be on this project? As mentioned earlier, Shane, optimize your thickness design. Analyze what type of material is available. Use the ASHTO Pavement ME program so that you can analyze the required thickness for the pavement and not over-design it and actually increase the carbon footprint when you don't need to. You can utilize these new program softwares like OptiPave, which allows you to design thinner pavements by using shorter joint spacings. And you can focus on performance rather than prescriptive mix designs. If you're specifying that you have to use a certain amount of cement in the mix design, and then it has to have a certain strength, you may be able to get that same strength by utilizing some supplementary cementing materials and decreasing that cement, so decreasing the carbon intensity of that pavement. Another thing is the leads points. Using the supplementary cementing materials, that actually gives you the ability to contribute to your leads, and using recycled material as well. And then the last thing is the pervious concrete contributes to stormwater management. There's, the last slide that I have shows you the pervious concrete. This material is a permeable material. It has a void structure of 15 to 25%. It allows the concrete to flow right through it. It is then stored in a granular storage area below the pavement. And if it has a subgrade that can allow that water to actually seep back into the ground, ground, you'll actually recharge the ground area. Or if it's a clay type material, you can just have the clay sloped so that you can collect the material, the water in the storage areas, and then you can use that water as gray water and use it for plants, etc. So another very environmentally friendly process. So that's it. Thank you very much.